Welcome. Good morning, good afternoon, good evening to everyone. Welcome to today's QED-C Quantum Marketplace. I'm really excited about the program we have this month. I think it really reflects the critical innovation that's happening in the part of the ecosystem that is feeding into some of the system developer and integration work. So fantastic crew that you're going to hear from, representing a lot of different parts of the world. The quantum supply chain is a global one, and QED-C reflects that, and the program today does as well. So I'm Celia Merzbacher, Executive Director of QED-C. I'm going to turn it over now to Mark Wippich, host of the Quantum Marketplace. Mark, over to you.
Great, thank you, Celia. So let's get into it. Okay, so today I'm gonna give some brief updates on the quantum marketplace, some overview and trends in the space. For components for quantum, we'll have a lineup of 6 presenters covering various areas, and then we're gonna have a roundtable panel discussion and a flash on some upcoming events. Okay, so the quantum marketplace is a place for raising brand awareness, facilitating collaboration, deals and partnerships, and that's been the feedback from the presenters and the audience as well in the past. So we have two platforms. One is a directory on the QED-C homepage under the Quantum Marketplace tab, which gives a listing of all the corporate members of QED-C that are providing commercialization technology to the ecosystem. And if you see a pink icon there, that means they've already presented in the quantum marketplace as well. You can click on their names, get a description, and or get to their website so you can connect with them. Also, all of these events are recorded, professionally video processed, and put on YouTube after. You can just type in quantum marketplace in Google and it will take you right there. So for today, again, all of this entire event will be posted on YouTube after. So today we have VexLoom, OE Waves, DFM, Yenoptic, Quantum Opus, and Single Quantum. So some overview and trends from components for quantum, and we call in this one components for quantum 2 because we've also run another quantum marketplace for components for quantum 1. I just flashed this is data that I put together in the past on the laser market that enables quantum 2.0. Really for 2023, it was around $150 million selling into quantum 2.0 applications. And even if we take a somewhat modest CAGR of 20%, that's still going out to well over $550 million in 2030. Now, what happens if we start looking at the photonics aspect of this and not just lasers? So in talking with companies that are doing quantum computing, networking, sensing, and quantum timing, and we start looking at how much the lasers actually comprise of the total bill of materials for their builds, and it's running somewhere between 15 and 30%, depending on the platform and the technology. But I just wanted to snapshot this out there that if we apply those metrics to the overall quantum 2.0 enabling photonics market, we're looking at about 600 million plus for last year, and if we apply that 20% CAGR out, we're looking at a $2.2 billion market in 2030. Okay, so for today, we're going to have 3 companies that are doing lasers in this space in the component level. They all have a unique approach and different wavelengths, et cetera, and you'll learn more about that. And then we have 2 companies today that are also doing single photon detection, and then we have 1 company that's doing modulation. So these components essentially are used in many of the the way that sort of we define the 4 segments in quantum 2.0, which is quantum computing, quantum networking, sensing, and timing. Okay, so with that, let's get into the lineup. Today we've got Phil McAtin, who's leading VexLoom's North America sales and service and support, and then we have Michael Carr, who's the CEO of DFM, which is associated with the Danish NIST. essentially, so Danish Metrology Institute, but they also sell products. We have Aaron Miller from Quantum Opus, which is a single photon detector platform. And then we have Ori Johnson from OE Waves, who's director of sales, and they're doing lasers. And then we have Jens Peter Ruska from Jenoptik, who is a modulator specialist that they're finding lots of home for in quantum as well. And then Katja Seal from Single Quantum, who's the VP of Marketing Innovation in the United States for them. Okay, with that, Phil, let's get your slides up.
All right, great. Thanks for the introduction. Thanks for the opportunity to be here, both to you and Celia. So I always like presentations like this to a slightly broader audience because I get to remind myself about these technologies that we're building. The solutions they're going to make are really going to be profoundly impactful on a global scale. And if you look at the modalities that people are using to build these types of systems and towards these applications, one of the leading modalities is based on what people like to call atomic physics. And so the way that I think about it, the way maybe to present it for this audience is that atomic physics is shooting lasers at atoms to engineer the quantumness inside them. And so Vexlum, as a laser company, I'm particularly excited about what we're doing because I think it's going to unlock a lot of solutions that people don't have. And to understand us, I think the best way that I like to do it is to think about the origin story of Vexlum. And it really comes from the pairing of a research collaboration of the laser and atomic physics, atomic clock, and quantum computing group at NIST, partnering in a collaboration with the semiconductor and laser group in Tampere, Finland, in the Optical Research Center, where after that collaboration, there was some of the world's best lasers made for magnesium at 280 nanometers. And 6 years later into that collaboration, this Vexlum was formed as a spin-out company in Tampere, Finland. We've grown organically over the past 6 years, and as Mark mentioned, we now have a Colorado office, which I'm leading as the first U.S. employee. So unlike many other companies, we're totally vertically integrated, where we do everything in-house for better or worse, and we've brought what we think is an innovative laser technology to the quantum research field. And so really the meat of it is that we are making optically pumped semiconductor lasers. Some people call them VXLs, some people call them optically pumped VXLs, some people call them OPSLs. But taking this technology that existed for a long, long time and applying it to quantum research. So you can see the semiconductor gain mirror on the bottom left of the photo that I have, or the diagram that I have there, which we make in-house, and then we use an optical laser to pump that, and we put a cavity mirror around that. And there's a whole bunch of laser physics and details I won't go into, but the result is that these lasers are very versatile. We can make the semiconductor material wherever we want to bake the cake. We can change the ingredients to hit whatever wavelength we want. They're high power. They're inherently have great beam quality, and they're inherently low noise and single mode. So by putting inner cavity elements, we can lock them to subhertz. Our partners have locked to subhertz clock transitions and done really cool things with these lasers. And so coming back to this idea of quantum physics or atomic physics is just shooting lasers at your favorite atom. What I did is I really wanted to convey the power and the breadth of the various wavelengths that we can hit. So take whatever your favorite atom might be, whether it's strontium for building atomic clocks, or it's ytterbium for building trapped ion-based quantum computers. Just go down the chart and pick out whatever your favorite wavelength might be, and that those are the powers in the systems that we're delivering right now or are in production right now. One way I like to visualize this data is just by looking at the spectrum and looking at all the various systems that we've delivered. And so the tagline that we've told many customers is that we can deliver a watt of power across the entire laser spectrum at low noise, single mode, single frequency. And we firmly believe that and stand by it. Some of the lasers, some of the recipes that we're baking for the semiconductor gain medium are still being developed and still in development. So the powers at those wavelengths are lower, but as time goes on, as we refine those recipes, the lasers will get up to that bar that we've set for ourselves and what our customers really want to see. So coming back to the lasers, we offer two products, the silver box and the yellow box. So the silver box we call the Velo. It's a research grade system that many users have in many atomic physics labs around the world. And then the yellow box is what we call the VXL, and it's a more ruggedized, more modular, more OEM type product that we're just beginning to launch in 2024. We've shipped a few prototypes of the system to date, but we're taking orders, but it's not out in the wild totally yet. So one last thing I'll leave you with, coming back to the slide of the various powers at the various wavelengths, is the images at the top. I took them from a bunch of iPhone photos that we have and just threw them up on the top of the slide with no color correction, no filtering, no nothing. It really, to me, exemplifies the fact that we are making these high power lasers at all these various wavelengths. And I'm a graphical person, so I really like to see these types of photos. I don't want to be cut off by Mark, so I'll just end at the thank you slide. And luckily I made it through my presentation without having to rush too fast.
Thanks, Phil. Okay, Ori.
Thanks, Mark.
OE Waves was started in 2000 as a spin-off from the quantum team at Jet Propulsion Laboratories. We spent the first many years doing research for a variety of government institutions and industrial partners, developing photonic technologies and a unique manufacturing capability. After building a patent portfolio of over 200 claims, we geared up to deliver products that help the quantum community. Let's look at a quantum system, the ytterbium ion. The ion has a quadrupole transition at 435 nanometers with a 3 Hz line width. Should one interrogate the ion with a traditional laser whose line width is broader than 3 Hz, only a fraction of the laser power goes to the interrogation, and the uncoupled light can be a source of noise and a loss of coherence. Should the laser go on the other hand, be narrower than the line width, the probing efficiency goes up, along with the ability to do fine control of the interaction. Our ridiculously narrow line width lasers have a simple structure. We start with a commercially available DFB or a DPR laser and couple it into our millimeter scale whispering gallery mode resonator. With a resonator Q factor of up to 100 billion, the self-injection locked laser has a Lorentzian line width as low as subhertz. The resonator is transparent from 370 nanometers out to 4500 nanometers, so we can provide a laser at any wavelength with an available diode in that range. In some cases, we need to double the laser to meet the customer's specific needs, so we're always looking for laser diodes, amplifiers, and doublers to be able to cover all required wavelengths. Lasers are often modulated for locking to a cavity or a spectral line. Various ways to perform that modulation introduce noise to the laser output due to tuning-related power variations. OE Waves lasers modulate the light by mechanically squeezing the cavity, moving the cavity mode without changing the laser power, leading to extremely low relative amplitude modulation. The small size of the cavity allows us to do this at high speed, providing over a gigahertz scan range with a megahertz bandwidth. As we all know, size and power matter, so these lasers provide this performance in a small package. The butterfly package shown at the bottom contains the whole optical system and is included in the cell phone-sized device above it. Having a single hertz instantaneous line width is a good starting point, but many quantum applications need the laser to be stable and low noise over a longer period. The stabilized cavity on the bottom right provides better than 10 to the minus 14th stability over 10 milliseconds. With that and the gas reference cell, our lasers can be stabilized for all timescales. While line width is a nice shorthand when talking about lasers, it obscures many aspects of the laser performance. Knowing the full spectrum of laser noise helps identify sources of decoherence and speeds up system evolution. We provide a homodyne multifunctional laser noise analyzer that's capable of measuring the phase noise spectrum of lasers with subhertz instantaneous line widths at a frequency offset up to 500 megahertz and relative intensity noise frequencies up to 40 gigahertz. Using photonic techniques, we have created a line of optoelectronic oscillators and voltage-controlled oscillators for signal generation in the gigahertz to terahertz range, with the lowest noise specs available for their size for demanding and emerging high-performance applications. These are complemented by phase and intensity noise characterization tools in the same frequency ranges. I want to highlight the optoelectronic oscillator in the bottom right. It contains roughly 30 optical elements in a package that's smaller than a penny. The design and development and integration of Capabilities that produce that package are available to the quantum market to help miniaturize the optical systems that are needed to scale up quantum computing and create smaller clocks and sensors. Outside of the lab, OEWave's products have been integrated into vehicles, flown into space, and sailed the oceans, so they're ready to go where the next quantum application takes you. We look forward to working with you as vendors, customers, and partners in system design and commercialization to remove noise from the quantum world.
Thanks, Ori. Michael.
First of all, thank you to QED-C for allowing us the time to speak today. My name is Michael Kjær. I'm Managing Director for DFM. So our role is actually a little bit broader than the other presenters we've heard so far. We are the Danish National Metrology Institute, responsible for developing and maintaining the Danish primary measurement standards. We do spend most of our day-to-day resources on developing new measurement science to promote the competitiveness of Danish industry. Our key activity today is within quantum metrology, and we are also very active in quantum standardization. We also provide test and demonstration facilities for quantum startup companies. And then, as Mark said, we do have a range of physical quantum products and also a range of accredited and non-accredited measurement services. We also do contract research. So this is typically where larger companies would come to us with a specific measurement challenge, and we can develop a solution for that on a commercial basis. And we are also very active in project collaboration and research. Quantum is such a big field. We certainly believe that if we are to be successful, if Danish companies are to be successful, we really need to work very closely internationally with other countries. So the specific solution and capabilities that we have at our company, we have a very narrow line width laser product, a line width of only 100 hertz. It is based on a fiber laser seed, which is then further stabilized to a gas cell. It is a product that we are shipping today with a lead time of 4 weeks. The primary application today is for atomic clocks, where it would be used together with a frequency cone. We are also developing other quantum products. For instance, we have something called a single photon calibrator, and this is an instrument that will allow customers to calibrate their single photon detectors. We're currently building a molecular beam epitaxy system that will allow us to grow quantum material. Our approach is a little bit different from many others in that we are building a very small but very flexible system that will allow us to really use many different types of gases, and also a system that really has state-of-the-art control of all measurement parameters. So we're not really going for volume, but going for something which is very versatile and hopefully will allow us to make something that is really state-of-the-art. For instance, state-of-the-art superconducting qubits that we can use then for reference qubits at other locations. We are also developing photonic quantum dots for single photon sources. And then, as I mentioned, we do have a full range of measurement and calibration services in nanoscales, dimensions, electrical potential, chemical analysis for light sources, optical powers, relative intensity noise, laser phase noise, and for PICs, it's things like loss and dispersion and modulation. So we are the strongest within photonics and nanoscience, and also in how those two fields actually relate to each other, and also how those two fields actually relate to quantum science. And I think this is the area where I think we can actually provide value to our collaboration partners. What we are hoping to gain from this presentation is always new research collaborators internationally. As I said, we believe that's critically important. We do not try and develop anything alone in-house. We always want to do it in close collaboration with other organizations. We are also hoping to identify commercial collaboration partners where we can co-develop new metrology products and potentially services. And of course, also looking for potential customers for our current range of products. Thank you for that.
Thank you, Michael. Jens Peter.
Ladies and gentlemen, welcome. My name is Jens Peter Ruske. I'd like to talk about the waveguide modulators which we produce at Jenoptik. Jenoptik is a photonics company with more than 4,000 employees, which is acting worldwide. The headquarters is in Jena, Germany. We have production sites in Germany, France, US, Canada, China, and other countries, and sales offices in many countries all over the world. The business focus is on optical components and systems for semiconductor industry, for life science, and for traffic safety. Some of the products can be used for quantum purposes, for example, different types of lasers, among others, laser diodes based on gallium arsenide. We have a strong micro.
Looks like we lost him. Okay, let's switch and go to Aaron.
It's my pleasure to present a little overview of Quantum Opus. We're a global supplier of superconducting nanowire single photon detectors, so very, very high performance single photon detectors and systems. It's a technology that has really been born on about 30 years of work, all the way from my graduate work at Stanford back into NIST, and then more recently in these kind of higher temperature superconductors that have really taken over the quantum world as the gold standard for photon detection. We're based in Plymouth, Michigan, near the University of Michigan and Detroit, which is very convenient for our manufacturing. I wanted to give you a little insight. It's kind of interesting to look at what happened to Quantum Opus's revenue in the last 8 years. It gives you a little view of who our customers are. Most of our customers early on were researchers, half of them in the academic sphere. So we work very closely with innovative researchers and respond nicely to partnerships with people who are really working at the forefront of quantum technologies in particular that require extremely high performance photon detectors. The other major part of our revenue was coming from government researchers, so FFRDCs in many ways, and government applications. And there it's been extremely valuable for us to have complete control over the manufacture of our systems, all the way from silicon, where we manufacture the devices from the ground up, design, manufacture those, install, test them, build our own systems, and ship very reliable and compact units for people who have demanding specs. But very recently, then, we've seen almost a quarter or over a quarter of our revenue in the last 2 years coming from where this community is kind of playing in this in the industrial area, which has been exciting because that's caused us to have to be a little more agile in what we do. So reducing our lead times and also just cycling very quickly with researchers and manufacturers in an industrial sector means that we're actually putting product into products rather than just into research labs. So it causes us to think about the specifications and the engineering of the systems much more heavily. So that's been pretty exciting. But in all of these, we partner very, very closely with our customers. What we offer are, as I said, kind of soup to nuts photon detectors, superconducting photon detectors that are nearly perfect. We can talk more about those if you're interested. We package them into compact and robust cryogenic systems that can either be desktop mounted or rollable, move around, wall plug and need nothing else, self-contained in all ways, 24-hour operation, hands-free operation, network controllable, so very convenient usage. But then we also push the performance of these devices and these systems very, very hard. So we can do billions of counts per second at 98% efficiencies and extremely good timing performance, 15 picoseconds, things like this. So we're always excited when a customer application demands something we can't do, because we can usually work really hard to try to meet those. And that's the way that we can work with you on your ideas all the way out to the implementation, which includes, in our part, a partnership with our customers after sale in software development or operation, training, installation, all these things that we're excited to do, because at the core, we're scientists and we really like spurring science by better tools. So that's what we end up doing. Most of our customers, especially early on, were in the quantum industry, as I mentioned. So we have customers in quantum networking, information science, quantum computation, photonic quantum computation. Also people who are integrating novel sources that require very good detectors. So that's a very good pairing commercially. We also have worked really hard on our sensing and metrology, and how do we know that what we're providing is what we're claiming we're providing? It's very difficult at the single photon level. So my background in NIST has really pushed us to try to understand our specs extremely well and be able to measure those at the single photon level. So we have a lot of expertise in that area. And we're starting to dabble now into more scalable technologies, integration of superconducting systems into other people's photonic processes. So those collaborations are coming in this commercial endeavor as well. It's also exciting that we have applications outside of quantum, free space communication, MarsCom with NASA, or in the medical technologies. These also benefit. They also help the quantum industry because higher volume here just means everything gets better for everybody. So that's pretty exciting. We've been super thankful for the beneficial connections within QED-C and the CQE that we were a part of, the Chicago Quantum Exchange early on, that has really merged together government research, academic research, and in industrial research, but also is spurring these industrial connections that we have that really we see as being the growth in the future. So how can you help, and how can we get what we need out of this? It always helps us to know what the industry needs are. If we don't know the need is there, it's hard for us to innovate and meet those. So we're really trying to touch base with everybody that we know to say, what's the driving need that we see 2 years in advance so we can help meet that. And second, we're always looking for partners, whether that's just partners in your commercial application, or if there's really a dominant growth path that we see, we're going to have to partner with people who can help us scale. So we're always looking for that sort of either co-investment or cooperation in terms of how we're going to meet those scaling opportunities as they come. This industry is scaling rapidly, and so we're not going to be able to do that alone as a small company. So more information, feel free to check out our website, Quantum Opus. There's our LinkedIn thing there. Appreciate your interest.
Thanks, Aaron. Katya.
I'm Katya Seal from Single Quantum, and I'm pleased to have this chance to talk about the work that we're doing. A little bit about the company. Single Quantum USA was formed this January and is a subsidiary of Single Quantum BV, a spin-off from the research group of Professor Val Zwiller, and is located at Delft in the Netherlands. What do? We make single photon detectors, SNSPDs, which have superlative specs for detection efficiency, signal to noise, and counting speeds. And this level of performance means that they're used increasingly in the quantum sciences for communication, computing, and sensing. And we've just heard a little bit about that from the previous talk. State-of-the-art SNSPDs will have detection efficiencies greater than 95, 98%, dark count rates less than 0.1 hertz, jitters of less than 10 picoseconds, and count rates in the gigahertz. And Single Quantum has met all of these specs. And we're the market leaders for timing jitter and for specialized electronics. More recent development projects include compact rack-mountable units, which are 10 RU footprint, number resolving detectors, count rates in the gigahertz, mid-IR photon detection, and free space cameras, also gating solutions. We have more than 250 systems worldwide. And so the question is, who's using our detectors? Quite a few people across a range of disciplines. And so too many to really mention, but I'm going to talk about a few applications to sort of give you a taste of the sort of science we've been involved with. So there's quantum communication, there's QKD over a 96-kilometer submarine optical fiber. I believe it's the first international demonstration of QKD, co-authored with Anton Zeilinger, a Nobel laureate at Vienna. Also, Toshiba has been using our systems for high-rate QKD over large distances. Computation, we're partnering with several key institutions for optical quantum computing. And there's bioimaging, where one of our cameras has been used by Hongji Dai at Stanford for deep brain 3D imaging in a live mouse. And it's the first demonstration of optical imaging with a depth greater than 1 millimeter in a living tissue. And the mouse was pretty happy, didn't suffer at all. And then our latest and most exciting at the moment is our deep space communication project, which is a partnership between the European Space Agency and JPL. And our systems are going to be in the communication between the ground station and the spacecraft that's been sent to Psyche, an asteroid that's more than 600 million kilometers from the Earth. So we're really excited about this project. It's been an exciting journey already. And I'll leave you with an old image of co-founders Val and Sander trying to deliver one of our systems in traditional Dutch style. We're trying to build Single Quantum USA with the same reputation of academic excellence and innovation that we have at Single Quantum Delft. And we're looking for collaborations and partnerships as we improve our service profile in the US as well. And of course, customers. So thanks for this chance to talk about our work, and please let us know how we can work with you.
Great, thanks, Katja. Jens.
Ladies and gentlemen, welcome. My name is Jens Peter Ruske. I'd like to talk about the waveguide modulators which we produce at Jenoptik. Jenoptik is a photonics company with more than 4,000 employees, which is acting worldwide. The headquarters is in Jena, Germany. We have production sites in Germany, France, US, Canada, China, and other countries, and sales offices in many countries all over the world. The business focus is on optical components and systems for semiconductor industry, for life science, and for traffic safety. Some of the products can be used for quantum purposes, for example, different types of lasers, among others laser diodes based on gallium arsenide. We have a strong micro-optics department with sophisticated lithographic technology for optical chip production, for example, for pulse compression gratings. The related systems are used for wafer inspection systems and semiconductor production machines. We have classical optics production for components and systems like objectives, beam steering modules, and cameras. Last but not least, our modulators. Integrated optics is a technology of integrating optical waveguides and devices. The aim is to create circuits like known from the electronics, but with optical function. Waveguiding is known from the optical fiber. Integrated optics uses waveguide structures in planar substrates to reduce the size and to use the special properties of the materials. The economical driver was the optical telecommunication, which needs lasers, modulators, splitters, switches, and multiplexers. Its wavelength is around 1550 nanometers. The necessary bit rates are in the 40 gigabit per second range. The optical power is several milliwatts. More and more applications come up which require other technical data. One example is the quantum technology. Our modulators are based on light semniobate single crystals. This material has a property to change its refractive index if an outer electric field is applied. A pair of electrodes is neighbored to a straight waveguide. The refractive index and thus the velocity of the light changes if a voltage is applied. So we have built a phase modulator. Its operation curve is linear. The phase modulator can be inserted into a Mach-Zehnder interferometer structure. It translates the phase information into an amplitude information. The operation curve is sine-shaped like known from interferometers. Such modulators are widely used in telecommunication to generate the binary optical signal. The Jenoptik modulators are similar to the telecommunication devices, but some modifications reduce the photorefractive effect, which enables applications in the visible spectrum and at higher optical powers up to 300 milliwatt in the infrared. We can provide modulators for custom wavelengths between 530 nanometers and 1750 nanometers. The switching voltage is in the range of some volts. The applications of our modulators are in laser technology, for example, to generate slice or pick pulses. Sideband generation is an important theme which is used in laser frequency stabilization or for optical clocks. The use of shorter wavelengths increases the accuracy in measurement technology. In the last years, we felt that the quantum applications are rising. Thank you for attention. Here is our address. It's my address, and it's the address of the North America Key Account Manager. Thank you very much.
Thank you. That's great. Thank you, Jens. That was great. Thank you, everyone. All right, so let's do the panel discussion here. So I'm going to start with Phil. What areas are are you mostly focused on today, and why, in terms of quantum computing, networking, sensing, and timing with your business?
Yeah, so most of the customers that we have are either in the quantum computing or the quantum sensing realm. So if you're building one of these systems, if I remember back to my good old grad school days, I always wanted the lasers to have more power. We were always limited by power. We were always limited by the number of atoms we could get or how fast we could do the operations. And so a lot of users have been really happy with getting the larger powers at whatever their particular wavelength might be. And it's really like we've had feedback from quantum computing, quantum information groups that just plugging the laser in right away, they've gotten the best Rabi flopping performance just straight out the gate without all the tips and tricks and things you have to play with these systems. So those are the main customers and areas that we've been focusing on.
Great. Thank you. Ori.
Yeah, our focus has been in quantum computing, especially as the really low noise has helped with our customers' fidelity in their gate operations. So the state preparation has been really improved by the low noise of the lasers.
Okay, great. Michael?
Yes, I would say for us, I mean, we're seeing so much potential come up in quantum technology. Today, where we have the most traction is, as I said, in time and frequency, and also quantum computing. Those would be the two key areas for us currently. But the other areas, both QKD and sensing, I think a lot of interesting applications will be coming there as well.
Yeah, great. Thank you. Jens Peter, so you had said in the past that you were seeing a lot of business in quantum computing. Can you expand on that, or are you also selling to other areas of quantum?
Yes, our focus is on the, let's say, strange wavelengths for the modulators. And so we have a lot of applications, in particular in atomic clocks and in laser frequency stabilization. We are driven by the customer's needs, and we try to fulfill the demands of the customer, in particular to the wavelengths. And I think we are the only supplier which makes modulators for the visible range.
Yeah, that's great. Fantastic. Aaron?
Yeah, since photons are used in all of these at some level, but mostly the computing, networking, and sensing all are kind of the photon-starved areas. So of course we sell into there. What we're starting to see as a bigger trend in the need is kind of interesting, is pushing out into the mid-infrared more, the 2 to 2.3 micron range. People are getting excited about, at least to see what kind of entanglement you can do between mid-infrared and visible. And so you really have a very, very poor single photon detection technologies out there. So we're starting to see that grow. And as I mentioned, the non-quantum stuff is growing pretty rapidly in the medical and other areas where you've developed a sensor for the quantum needs, but it's now actually visible to everyone else as being drastically better than what's on the market.
Yeah, and so one distinction here, right? Because not everybody knows what single photon detection is for, but with you and single quantum, I mean, for Quantum Opus, you're specifically primarily nanowire. You're using cryo and that sort of thing to get super high sensitivity in your single photon detection. Is that true, or you're also getting out of cryo too?
No, we're definitely focused on the cryo end of things. We've thought about other technologies as well, and partnering with other technologies there. Because of our expertise in the timing and the electronics, we could probably do okay there. But right now, there's such a demand that we actually can't meet all the demand at this point. We're working on. That's part of the scaling thing. That how fast do you scale? You don't want to get growing too fast, but there seems to be a high demand, and there's pressure, as I mentioned, to drop lead times. The cryogenic supply is pretty poor, and so to manage that supply chain, to drop our lead times from 30 weeks to 20 weeks to 12 weeks, and this is the pressure, is to try to just keep pushing things shorter and shorter, and that's where I think we're gonna be a little bit better off, is just trying to manage what is really not a quantum problem, but is a logistics problem at some level.
Well, hopefully some of the quantum hub funding that's coming is going to help with that.
Yeah,
so
that could.
Katya.
Yeah, so I was saying, as Aaron mentioned, certainly scaling up is a challenge with suppliers and cryogenics. We all face this common issue. At Single Quantum, our focus, I think we're trying to capitalize on the fact that we use niobium titanium nitride, which has a really fast recovery, and so we're trying to push the forefront of speeds, counting speeds and jitter. That's what we're known for, and that's what we're focusing on. And apart from some of the other stuff, but I'd say that the timing and also imaging capabilities, where you do multi-pixel for arrays, because we got really good electronics. So I think these are the two areas that we're trying to push.
Okay, great. Thank you for that.
Sure.
All right. So in terms of, we're starting to see some of this. So that's why I like to ask this question. This is, more of a commercialization panel here and a little less on the research. But so for Quantum 2.0 system solutions, they require leading edge hardware components in terms of performance, reliability, and really starting to have ruggedness too in the various operational environments. I want to go back to Aaron. I mean, Aaron, you said that you started out selling to universities, then you're selling to government labs, and now you're actually starting to sell to commercial customers. And so how are you dealing with the challenge of ruggedizing your platform?
Yeah, it is a challenge that hasn't been fully met. Definitely be honest about that. When you're only dealing with, we hired a manufacturing engineer, and he very quickly said, we're not a manufacturing company, we're an R&D company, because we're not manufacturing 10,000 of these yet, right? So part of that shakes out, no pun intended, as you do a lot of this shipping and having 200 systems in the field. We kind of know what fails in shipment, but we've had some requests to change the way that packaging is done to meet some sort of environment that it's going to go into. And that actually causes us to think a little bit differently about what the components and materials we use to test those before they go out. So we're starting to get that direction, but still in the volumes that we're talking, when you're 10s to 20s to 50s of things, it's really difficult to come up with a process where things don't change and have been tested extremely well. That's where, if we talk about scaling into markets that require thousands to tens of thousands, now you do things differently, and so that QA transition is something that we've not had to do yet. So far things are very good, but we haven't really. People have asked, what happens if you shot this into space? Well, it wouldn't function there, because the way that we do our system, it was meant to be affordable on the ground. And so things are engineered very differently depending on its environment, and that we haven't had to come to in an aggressive way yet.
Yeah. Thank you for that. Katya.
Well, portability is certainly an issue when you have a cryogenic platform. It's something we're working on. I don't know that we have a ready solution yet, but our systems have been moved around in trucks and taken from, we've established them in data centers. So we're getting better at it. But certainly I'd say that starting from the ground up, device fab is still a challenge to get good yields and to really scale up from that point on. So I think we're trying to focus on that too as the fundamental, starting point.
Yeah, great. Okay, thank you, Ori.
Yeah, so a couple of things in terms of like vibration. Our systems are extremely vibration insensitive. It's really fascinating to see the data on that. But then temperature is a totally different beast, and it's a challenge that we're working on meeting that the customers' needs for how hot their environments are, how cold they go. And also moving out of the laboratory for all of the products, moving out of the laboratory into the field and saying, okay, yeah, the lab laser that I'm using in my experiment, it can go, it can unlock once in a while. That's fine. But when you're running a commercial computer, it needs to be on for a couple of years without anybody touching it, and so that's a different challenge, and so we still got some work to do there, but we have a good plan going forward.
Okay, great, Michael.
Yes, I have to say, for us, reliability is such a key issue, and maybe it's because we're the National Metrology Institute, so we're actually typically a little bit slow to push new products out to the market until we're really sure about the reliability. So the way we usually go about it is to have an end user that we're working really closely with, which can really test our products and solutions for some time before we actually go and have a general market introductions for new products.
Yeah, great. Phil.
Yeah, so I think a good way to characterize our products is that we've really been pushing on the performance, and the users have come back and said, oh wow, these are really great performing products. And so that was 2, 3, 4 years ago. And as you saw in the presentation, now we're making this transition to focus on the reliability and the ruggedness, and coming out with a smaller, more modular, more easily replaceable, more easily serviceable product. And so that's exactly where we're driving our company, and that's what people want. They want things to be able to be turnkey and turn the key and forget it.
Yeah, great, thank you. So Jens Peter.
Yes, our modulators are similar to the telecommunication devices, and there have been a lot of investigations concerning the reliability, and we can benefit from them. So we have no problems with the ruggedness, but we try to increase the performance concerning the guidable optical power, especially in the visible wavelength range, and maybe to shorten the wavelengths. Today our shortest wavelength is 532 nanometers, and we try to come into the blue range.
You have quite a bit of experience doing this reliability and ruggedness testing and qualification because of telecom, right?
Yes, we can benefit from the telecommunication companies, and we can benefit also from the experiences. There have been made a series of tests concerning the ruggedness in the past, and we can benefit from this.
Yeah, great. Okay. So in terms of your customers, right? So I'm going to go back to Phil on this. What are your quantum commercialization customers getting out of your solutions today?
Yeah, so I shared that testimonial earlier where one of the customers plugged our laser in, and it had the best performance that they've had to date, and just kind of straight out of the box. But that's really what we're driving towards, is that all these atomic-based systems, they are driving to increase the performance, right? We're all trying to get to quantum advantage, and then for many of like Vexlum's customers, the performance of the lasers, if you can improve the laser, it directly translates to better performing systems. And so that's where we're focused. We want to get better performing lasers for our customers, so their systems end up performing better. And a really good example of that is just very recently, within the past year or so, we've now started integrating electro-optical modulators inside the laser cavity that I described. And so now people can use these lasers, or use that EOM as a very, very strong lever arm to lock sub-hertz type of line widths for our systems.
That's great, and I think what's unique about Vexlum is even though that you're a small company making lasers, you have a lot of the visible wavelengths, you have a lot of the powers that are not available from all the laser suppliers, correct?
Yeah, and that's it might sound a little cliche of, oh yeah, we can get a watt of power anywhere, and I was skeptical too before I joined the company. But really looking at the data, you just start stacking up the powers at the various wavelengths, and it's really kind of eye-opening of, oh, if I can get a watt at this magic wavelength, or this clock transition, or this Rabi flopping transition, all of a sudden your systems can perform faster. You can have more zones. You can do longer clock integrations or interrogations or all those things. So yeah, it is nice to be able to say, oh, we cover all the wavelengths, and then throw a picture up there and say, here's our orange laser, here's the yellow laser, here's our blue laser, here's our violet laser.
Yeah. Thanks for that, Ori.
Yeah, so it's really in the fidelity and quantum experiments, and also simplification of systems. I look at like the room at Gilla that hosts the narrow line width laser there. That performs slightly better than our cell phone sized device. And being able to simplify customers' experience systems by plugging in our lasers and reducing a lot of the noise and locking systems they have in place with the with version of how we do things. The squeezing of the cavity is a really interesting feature, like I mentioned earlier, that allows us to give really fast tuning with extremely low amplitude modulation, and that has been really helpful to our customers.
Yeah, great. Jens Peter.
Yes, it is one of the advantages of our production principle that we can ship modulators for special customers' needs very relatively quickly. We can grab into the shelf and we can put there the chips for almost any of the wavelengths between the green and the 750 nanometer range. The construction of our modulators is like a kit. We have a set of different instructions on every chip. That's so we can adjust the wavelengths with an accuracy of approximately 10 or 20 nanometers, and that is enough to fit the customer's wavelengths. And so we often see that the wavelengths, for example, of the customers for atomic clocks are very specific, let's say 689 nanometers or something in the range of 705 nanometers. And it's very easy for us to pick up the chips and to make the pigtailing from them. We have the set of the chips in the shelf, and we finalize the modulators after the customer's demands.
Yeah, great. Thank you. Katja.
So as we started out more with the academic market, I think like many of us, and now as we're moving more towards commercial customers, we're looking at modularity and the user interface. We worked a lot on our software, but at the same time, we still have the flexibility to work on specific solutions because we have some real strong electronics wizards on board. So we've developed customized electronics that we're now starting to commercialize. So I think that's sort of got both components going here, essentially.
Great, thank you. Aaron.
Yeah, one of the things in the big picture that I think our customers, and especially our commercial customers, really want is they want to know what's possible. And because they're planning 2 years ahead in terms of their products, and the specs of their final product or their final research, if it's a researcher, is highly dependent on the specs you can deliver. And so we work really hard to be very believable on our specifications, but also to deliver what's needed for their specific application. So we can make a full custom nanowire wafer, hundreds of devices, fully screened and tested within 10 business days. So what that means is that someone has something that's hard, but they say, we didn't know that you could do UV or you can do these other things. It just changes what's possible. And so they change what they can do in terms of their output. And because that's so easy and quick, it becomes very natural for us to hit kind of very demanding applications that other people had not even thought about. Even just using the systems, as Katja knows, when someone gets a nanowire system and they've been using InGas, their light goes on, they're like, oh, I can do a measurement now in 2 weeks that would have taken literally 2 years of measurement time. This changes the way you think. So this can happen also just by changing the technology type. The technology is actually extremely flexible. And so we just have to figure out how to apply it best to your application.
Yeah, great. Thank you. Michael, you're selling this stable laser. You mentioned that you combine it with a frequency comb, and a customer can now have a commercial customer can now have an actual optical atomic clock.
Yes.
Right? So can you expand on that, because that's kind of earth-shattering, right? We've been talking about that for 20 years, and there's a lot of talk around this, but you can just do that?
Yeah, so we can do that, and I think it's based on a frequency comb from the company Wesson Photonics and our stable lasers. So we've been developing this stable laser product for a number of years. So it is really by now really well tested. It has a very high reliability. Customers can just basically put it out in a box, turn it on. It's a turnkey solution, and then it will operate literally for years without any problems. And combined with the frequency comb, I think we've been able to come up with a combined solution that really has some very interesting specifications and something that is significantly better than Mesa solutions.
Yeah, great, thank you. Okay, so Phil, what is your company's biggest challenge in succeeding in quantum? You're probably selling lasers into other markets as well, but what's your biggest challenge in quantum 2.0?
I mean, that's a good question, Mark. I don't know that there's like a clear answer, because right now where we are is not where we're going to need to be 2, 3, 5 years from now. And so I think some of these problems take a lot of time and take a lot of iteration. And so I think it's just it's getting enough time to really dial in the recipes that we grow these semiconductors at to provide the chips that everyone needs. And so I think everything's done in-house, and so that's a blessing, because you get to control the process and make the gain chips and the lasers as as you want to your specifications, and as people use different atoms and ions, we can provide solutions to that. But it's also a curse that that cycle time and that iteration time is something that we just need to stay on top of.
Yeah. Thank you. Ori.
Yeah, in contrast to Phil, we don't make our own semiconductors in-house, which gives us greater flexibility, but also we lose control over the manufacturing process.
You don't have control, I would say, right?
Yeah, exactly. We don't have control. That's right. And we trade flexibility in terms of who can supply what to us for the control of what they are doing, and therefore, so our big issue is hitting all the wavelengths, because the quantum market is still so wide in terms of the ion or atom or whatever the material system of choice is. And so being able to hit everybody's spec with the power that you need, their wavelength with the power that they need, that's our biggest challenge right now.
Yeah, great. Thank you. Michael.
I would say for us, it's continuing on the track we're at right now, developing new and better products. So for instance, for quantum computing, we are also developing lasers, which are going to be high power, ultra narrow line width, and a range of wavelengths that are going to be needed. So of course, all these things is a huge challenge in itself. So being ahead of the development, I think, is our biggest challenge.
Yep. Jens Peter.
Yes, our biggest challenge is the following. Jenoptik consists of a lot of different subsidiaries which are producing a lot of products which may be used for quantum technology, but they do not work together until now. For example, in the moment we are building a new fab in Dresden. It is 2 hours east from Jena, which works on the micro-optics field. They have almost all what is needed on lithographic technology, for example, e-beam technology and photolithography and etching technology and all what you can imagine in microstructuring. And our aim is to integrate and to bring these technologies together. We can make laser diodes and gallium arsenide, we can make micro optics, we can make modulators, we can make classical optics, but we have to integrate and to miniaturize these technologies to make new products. The difficulty is that it's not really clear until now what the quantum technology really needs and what it's can be produced in a big scale. And you must be very flexible to follow the possible development lines which maybe come in the future.
Yeah, and then also managing where you can adjacent markets, right? So, Aaron.
Yeah, I think it's a common theme here that we're on this growth curve in the technology adoption. And the problem is in that growth stage, there's a proliferation of needs because we've not focused on one killer market or application. And so whether it's sources or detectors, we could probably all scale and meet the need if there's only one dominant need. The problem is every researcher has different things to push the boundaries of what they want to do. So nobody's doing exactly the same thing. So, to meet that whole need, you're necessarily customizing things and you're not a manufacturer at that point. So if you really are going to make 10,000 units of something, it has to be to hit a very known market. I don't think we know what that market is yet.
Yeah. Okay, Katja.
Yeah, I think Aaron stole my words. So
That's fine.
It's not a mature market, and so scaling up is hard because you don't know which direction to focus in, and that's sort of where it is.
Yeah. Okay, great. So let me actually flash some upcoming events. I think that's a wrap on our session. We're going to do this partnering conversation after. So QED-C is going to have a plenary in Chicago at Northwestern Technology Institute, and we've lined up a live event in partnership with Duality. So we're going to have Crystal Lakes, Great Lakes Crystal Technologies, QBraid, QuantCat, MEMQ, and Icarus Quantum. So if you're interested, definitely follow up with QED-C to see if you can attend that. Celia, you have any final words on this part?
Sorry, trying to find my camera. Thanks, Mark. And I will just make a minor correction for those who are familiar with Northwestern. It's not a technical institute. It's Northwestern University, but great engineering programs.
Needs to be updated then. All right. So
okay. Thanks for flagging. No, we're really excited to be visiting Evanston, Illinois, just outside of Chicago. In March, and it is a hybrid meeting for members, so you can attend even if you can't travel to Chicago. And for those who aren't members but are interested in maybe becoming one, contact us, and we welcome you as well. So I want to wrap up with saying thank you again to all of our presenters today. It was a fantastic program.
Yeah, thank you.